Okay, class, today we are going to talk about elimination reactions. So these are the sister or brother reactions to substitution reactions. And the reason I say this is because the components of each type of reaction are very similar. So in an elimination reaction, you will have some type of alkyl halide. You will have a base of some type. Call this R, so base. And of course, a solvent. I will draw this solvent. And the main difference between a substitution reaction is that instead of a base for substitution, you have a nucleophile. And remember, nucleophiles are Lewis bases. So the components are very, very similar. The reactions, though, the actual products are quite different. So in a substitution reaction, of course, you substitute the nucleophile for the leaving group. In an elimination reaction, what we end up forming are alkenes. And we have our leaving group. And whatever our base happens to be, this will be, it'll end up getting protonated. So in the case of the example above, this would be the conjugate acid, now that it's been protonated from the reaction. So just like in the substitution reactions, there's two types of elimination reactions. There is the E2 elimination and the E1. And just like with the substitution reactions, they are going to be very similar in their mechanisms, their rates, and the conditions by which these things take place. So the rate of a E2 elimination is equal to some rate constant times the concentration of your alkyl halide times the concentration of your base. So this is a bimolecular reaction. It involves the collision of the base with the alkyl halide. The elimination reaction, the rate determining step, the rate is some rate constant times Rx. So it's only dependent upon the alkyl halide. So this will be a unimolecular reaction. So these two exactly mirror SN2 or SN1. So they're exactly the same type of thing. So in an E2 elimination reaction, what we are going to have is our base, and I'll just use B with the 2 electrons. It involves the collision with your alkyl halide, just like this. And so in this reaction, the base is going to remove a proton, and you will notice something important here. The proton is on the carbon next to the leaving group. So this is the carbon with the leaving group. The proton is on the carbon next door. That's important. Okay, So it's going to grab that proton. These electrons are going to move between the two carbon atoms, and that's going to form a pi bond, and the leaving group is going to leave with the electrons in that sigma bond. So we've got, so our products will be the H, our alkene. Let's draw this a bit better. Alkene. And our leaving group. Now, just like in an SN2 reaction, there was a stereochemical requirement with regard to an SN2 where the nucleophile had to attack from the opposite side of the leaving group. In this case, what we're going to see is there is a stereochemical requirement of which proton can be removed. But we're going to get back to that in a second. Let's do the mechanism, the unimolecular mechanism of a E1 elimination next. And so in this case, it's only dependent upon the concentration of the alkyl halide. So let's make an alkyl halide here. And again, in this case, we're always going to be removing a proton from the carbon next door to the leaving group. So I've specifically drawn this carbon, not as an R group, but in this case as a methyl group, because we'll see that in a second. Okay, so the first step will be, just like in an SN1, the leaving group leaves. So this will be the rate determining step. And what will we form here? We will form a carbocation. So this carbocation is going to be high energy. So remember, we're going to, and I've specifically drawn a tertiary carbocation here because it's the lowest, it's the most stabilized, right? So how do we stabilize carbocations? One, alkyl groups, they donate electron density through induction. And two, hyperconjugation. And here, this little proton would be hyperconjugating with that positive charge, that empty p orbital. So again, so tertiary are more stable than secondary, which are more stable than primary. So in this example, I've used a tertiary specifically because of that. Okay, so the next step of this reaction is going to be that our base is going to remove our proton, and it's going to specifically remove the proton, which is any protons that are hyperconjugating. And if you've got three alkyl groups, you could have three groups that are hyperconjugating. This will go there, and we will form our product. So this would look like this. So I've drawn this alkene with the wedges and the dashes. In this, from this perspective, we're looking at it sideways. But if we were to draw it, if we were looking at it from above, it would just look like this: R, R, H, H. Okay, good. So there would be a rate determining step, which would be slow, which is the leaving group leaving. And then the second step, the removal of that proton, would be fast. And so if we were to then draw the energy diagrams of each of these mechanisms, the E2, this would be free energy. This would be the reaction coordinate. The E2 would look, that line isn't particularly smooth. Let's make it a bit smoother. It would look something like this. Delta G naught. Let's have delta G dagger, or the activation energy. And this would be very, 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 very similar to an SN2, right? So the E2 energy diagram, this is E2, looks almost exactly the same as an SN2. Now the transition state here, this of course would be at the top. This would be the transition state. Of course, you couldn't isolate this, but it would look something like this. So we would be forming a bond between the base and the proton. We would be breaking the bond between the proton and the carbon. We would be forming a bond between the two carbon atoms, and we would be breaking the bond between the carbon and the leaving group. So it would look something like this. Where we're starting to form the bond we're starting to form is our pi bond, and we're starting to form the sigma bond here, and we're breaking the carbon proton bond, and we're breaking the carbon leaving group bond. So that's what the energy diagram of an E2 elimination would look like. So it's very similar to an SN2. Let's do something similar for our friend over here, the energy diagram of an SN1. Okay, so our rate determining step is the leaving group leaving to form a carbocation. So this would be our carbocation intermediate. And this would be our transition state here. Transition state number 1. And this will be a late transition state. So it's gonna resemble the carbocation intermediate. The second step, which is fast, will be formation of our alkene. This will be our starting material. And at the top here, this would be transition state number 2. And this would be early. So it would also resemble the carbocation intermediate. This would be our delta G naught. And our activation energy would be delta G dagger, activation energy. So you'll notice here that in an E1 elimination, the first step is the formation of this carbocation. Well, you remember back when we did our substitution reactions, this is the first step of our of an E1 and an SN1 reaction. So the first step is identical for both of them. So I've drawn a pathway here for the formation of an alkene. There would also be another pathway, potential pathway, which would be the formation of, let's do this in green. There could be another pathway, which would be the formation of the SN1 product. Now, depending upon the reaction conditions, this product could be higher or lower than the alkene, and the energy for the transition state could be higher or lower for transition state number 2. The rate determining step is always going to be transition state number 1. So depending upon what if you've got something which is more of a base than a nucleophile or more of a nucleophile than a base, then you could see these two products here you could get a substitution product or an alkene product. But the first step is exactly the same. So those are basically the mechanisms and the energy diagrams of our two types of elimination reactions. And so yeah, so that's basically the two. Now there's some key points for both of these. So if we remember about alkyl halides here, we could have primary, secondary, or tertiary. SN1 reactions and SN2. So SN1 happen readily with tertiary and happen slowly with secondary. And it didn't happen at all with primary. For SN2, they happen readily with primary alkyl halides. They happen slowly or slower with secondary, and they didn't happen at all with tertiary alkyl halides. So if we were to put in what we're doing next, which is the E1 and E2, E1 is the easiest one to do because these will happen because the first step is exactly the same as a SN1. These are only going to happen under tertiary conditions, and it's going to be very slow with secondary, and it's not going to happen at all with primary. So we're going to see that SN1 and E1 are basically very linked together, and really the difference between the two of them is going to be dependent upon our Lewis base. Lewis base. Is it a nucleophile? Then it will be SN1. Is it a base? Then it will be E1. But there's some special conditions on that as well. Now, the thing which is different from all of these, which we'll see, is that for an E2 elimination, this is possible under all conditions, the E2. And so the difference between an SN2 and an E2 reaction taking place, we're going to have to look and see, do we have a strong base or do we have a strong nucleophile, and what are the solvents? So we'll get back to that in a little bit. So, but the key point for an E1 is that they're only possible under the same conditions that an SN1 reaction is possible under. But let's look at the E2 next in a little bit more detail. Okay. Details. Okay. So just in a SN2 reaction, the nucleophile had to attack the leaving group on the opposite side. With an elimination reaction, the proton that is removed, there's a specific requirement for it. So in the previous example, how I had drawn this, and let's use bromine as our leaving group. And let's put methyl group here, H there, H, methyl group. What will we put? Let's put ethyl group. No, actually, no. Let's put a proton here. So in the previous example I showed above, and let's have our base is just going to be hydroxide. I specifically removed the proton that was here on opposite sides of the leaving group. And then these electrons moved here, and then these electrons moved there. And so in our SN2 reaction, remember, the electrons were moving into the sigma star orbital of the carbon X bond. Here, this, let's change this color of this arrow to blue. These electrons, when they're forming the pi bond, are moving into the, see, the sigma star orbital of the carbon bromine bond. And to do this, this proton has to be on the opposite side of the leaving group. So if we draw this as a Newman projection, and this, it'll all become crystal clear when we draw this as a Newman projection. So here's our eyeball with our eyelashes. And let's use green. And we're looking down this bond here. So our back carbon, front carbon. Bromine is straight down, Br. On our left-hand side is a proton. Our right-hand side is a proton. On our left-hand side is a methyl group. And then the proton is up, the methyl group, and a proton. So the circled proton on the drawing on the left is here. And you'll notice that these two groups are anti. So the requirement for an E2 elimination reaction, the requirement is that the proton and leaving group must be anti. So they have to be on opposite sides. Now there's a higher energy one where the proton can be removed. So this would be the low energy. So the higher energy version of this would be as follows. We would have to rotate our molecule 180 degrees. So the high energy version we are going to rotate bond 180 degrees. And we're going to see then that the bromine H back stuff is still the same, the methyl and the proton. But on the front, the methyl group would now be over here and the H would be over here. So this would be the high energy. So this would be eclipsing. That is a possibility. But the key point here is that both of these groups are still lined up. They're eclipsing. Over here, when they're anti, if we were to draw this, they are lined up. So an E2 elimination, the low energy one, which is most things will take place through the low energy intermediate, this requires that proton plus leaving group must be anti. So for most of the, unless your molecule's got some symmetry associated with it, or some chirality associated with it, most of the time there'll always be a proton which is anti to it. But there's a couple of really important examples in which there's only one proton which will be available. So just as we brought back our friend the Newman projection here, Newman, when we were doing Newman projections in the past, the next chapter was when we had cyclohexane derivatives. So let's go back and look at some cyclohexanes and see how these eliminations will take place with them. Okay, so here's an example. This compound here is called neomethyl chloride. And if we were to draw the two chairs of this, let's do that. Let's remember how to do that. Okay, so we will do our typical numbering 1, 2, 3, 4. 1, 2, 3, 4. So on carbon 1, we've got an isopropyl group and it is up. So in this conformation, the isopropyl group would be up. Carbon 2, we've got a chlorine which is up. So this will be equatorial, which is up. And then on carbon 4, we've got a methyl group which is down, methyl. So this one, we've got two axial substituents, which are, particularly the isopropyl is this one's big, right? That's not good. So this equilibrium, when we draw, okay, let's do the other one first. Okay, so carbon 1 here, 1, 2, 3, 4. So remember, what was axial will become equatorial, and what was equatorial will become axial, and they will still stay up or down depending upon what they were. So carbon 1, isopropyl group up, but it's now equatorial. Carbon 2, the chlorine is up, but now it is axial. And on carbon 4, methyl group, which is down, and it's gone from axial to equatorial. So let's erase this equilibrium, because this equilibrium is going to strongly favor this direction, right? This little arrow will be. So this will be the favored conformation because large group is equatorial. Okay, now, when it comes to an elimination reaction, an E2 elimination reaction, the two groups have to be anti to one another. So in cyclohexanes, this means that the leaving group must be axial. It has to be axial because when it's equatorial, a bond is where the proton needs to be. So if we draw, so here on this carbon, on this the proton's going to have to be axial as well. So there's there's two protons here which are both axial on the carbons next to the chlorines. On this conformation on the left, there are no protons anti to Cl. And the best way to do this, to visualize this, is to draw a Newman projection of a cyclohexane ring. And let's see if we can do this quickly. So on a cyclohexane ring, the substituents here are the equatorial substituents, and the substituents here are axial, and these ones here are axial, and these two would be equatorial. So if we put in a leaving group, let's put in a leaving group, you'll notice that the group which is anti is actually this carbon bond. So there's no proton there. And let's draw a couple protons. Let's put a proton here, H. Now, when we do a ring flip, what's going to end up happening is that this now is down instead of up. And then the back carbon is up instead of down. And so the leaving group is going to move up, and this proton is going to move down. So on the back carbon, you've got your proton, H. And on the front carbon, you've got your leaving group. And they're now axial, and now they're lined up. So now they are anti to one another. So they can be eliminated. So the key point on a cyclohexane ring is that the leaving group has to be axial. So the leaving group must be axial. So in this conformation we've got over here, there's actually two protons that can be eliminated. So your base can come along and grab this proton to eliminate that chlorine. Or your base could come along and grab this proton and eliminate your chlorine. And this is actually going to give us two completely different products. I'll draw the green product over here. So this is the green, and the orange product would be as follows. Comparing that to original molecule over here on the left, the neomental chloride. So remember, it's on carbon 2 that is where the leaving group was, and you're always going to form a bond between, it's always on the proton next door. So that's why there's carbon 2 is always going to have a double bond. It's going to have one end of the double bond, but it can be in either direction. So actually here we've got these two structures, the green structure and the orange structure. They are basically, they're constitutional isomers. Right? They've got the same molecular formula, but different connectivity, right? They're not mirror images of one another. The double bond is located in a different position. Okay, so we're going to see in a second that one of these two is favored over the other. But the first part, the important thing is that the leaving group has to be axial on a cyclohexane ring, and the proton has to be axial on a cyclohexane ring. Now let's look at a similar reaction with a stereoisomer of neomethyl chloride, which is methyl chloride. Okay, so methyl chloride looks like this. Isopropyl up, chlorine down. So this is a diastereomer because in the previous example, the chlorine was up. The methyl and the isopropyl are exactly the same. So if we're going to translate this into two chairs, we would have these two chairs. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Up, down, down. Up, down, down. So you'll notice that on one of these two conformations, we've got all axial. And the other one, we got all equatorial. So one of these is clearly going to be the favored conformation, and that's going to be the one on the right-hand side. But in the all equatorial conformation, no elimination is possible. Because the leaving group isn't in an axial position, right? So no elimination is possible. When, however, the conformation changed to make this chair here on the left, this one, let's redraw this over here. And this is important. You will notice that in this case, if this chair was to flip to go to this high energy conformation, there is only one proton available to eliminate. Because on the other carbon next door, there's this isopropyl group, which is blocking it. So the base can only eliminate one product. And so, can only grab one proton. So we're only going to form, potentially, there's only one possible product that could form, which would be this one. Only product. Whereas in the previous case, technically there were two products that are possible, and depending upon the base you used, you could hopefully tailor it to get the one you'd want. This one over here is when you use like hydroxide as a base, this would be the major product. Okay. So if we're ever doing an elimination reaction with a cyclohexane, the key point is that the leaving group and the proton both have to be axial. And sometimes the it's like in this example here, this reaction would be very slow because this is a high energy conformation, and you'd have to flip into that high energy conformation. And so this reaction could be an exceedingly slow reaction. So key point, in the cyclohexane, the leaving group and the proton have to be diaxial. Each has to be axial. Okay, so now there, as we said before in that example here, there were two possible products that could form in the first example. Now let's just do some examples on just a regular secondary, on a regular secondary alkyl halide. So if you've got some base, there are a couple of things that could happen. So there are 3 protons here on this carbon, H, H, H. And if we were to draw this guy, let's draw this guy forward. That would mean that the group which is anti to it would be this proton with the dashed line. And we had H, H. So when we have our base, there's 2 possible products that we could form. We could grab this proton and eliminate it to make this product in purple. Or we could make a line with blue, no, not blue, green. Space could grab this proton, go there, that could leave. And in this case, we would make this alkene. So 2 constitutional isomers. Now, it turns out that the main product is the alkene with the most number of substituents. So this tends to be the major product. There is the cis version of this as well, which is another complicating factor, but for the main point, we'll just draw it as a trans product. This is the main product. And we'll call this Zetsiev because it was this Russian Zetsiev's product who discovered this when we were doing elimination reactions. So this tends to be the major product, particularly if the reactions are done under thermodynamic conditions, because the more substituents you have on a double bond, the more stable it is. The product where we've got on the terminal carbon here, this is Hoffman's product. So there's a way of determining which product you will make. So alkene stability So the more substituents you have, this is more stable than, say, a tertiary one with 3 substituents, which is more stable than 2. And there's approximately the same as which is more stable than 1. Trans tend to be, just for steric reasons, trans tend to be slightly more stable than cis, which tend to be slightly more, these two are very similar. But the mono double bond is the least. So, and this is really because of, you can look at this a couple of ways. One is bond strengths with the orbitals being used. And the other one is hyperconjugation. So there's alkenes can be, hyperconjugation is probably we'll dig deep into this at the start of next term, so don't really worry about that right now. The key point is that when this type of reaction was first discovered by Zetsyev, this was the main product was alkenes with more than one substituent versus the ones with only one. But there's a way to tailor your reaction to allow the Zetsyev product to be the major product or the Hoffman product to be the major product. So let's do the Hoffman one first, because that's easier thing to look at. Okay, so let's pretend that we've got a so the best way, so remember, E2 eliminations, we need the base to come and grab the proton, which is going to cause the leaving group to leave. So let's make a base here. Draw a base. And let's make it something that is a very bulky base. So this tert butoxide. So this is bulky. Remember, this is something which can only behave as a base. It really doesn't behave as a nucleophile at all because it's so bulky. So we are going to come in and it's going to be part of the transition state. This is going to grab this proton. These electrons are going to go here, and then that's going to leave. And so when you use bulky bases, you tend to form Hoffman products. So you need a bulky base. And we are going to draw the removal of the other product with a bulky base to show why. So what this is going to do is this is going to destabilize one of the transition states. And this transition state here, this is the low energy version. So this is low energy. Low energy. To do the high energy one, let's redraw this out here again. X. Now we've got it's this carbon. So remember, it's this carbon here. So let's draw X. Now we've got we won't draw out all the protons in this methyl group. Carbon, now we need a proton here. We'll draw H in the R group, because originally our thing over here had all this 1, 2, 3, 4. It was a propyl group, so this would be an ethyl, I guess. Ethyl. So to make the most substituted alkene, our tert butyl group, our tert butoxide here, negative. It's got to come grab this proton, those electrons go there, and that leaves. And when it's trying to grab one of these internal protons, I'll call this guy here internal. Now there's potential steric interactions. So it could be bumping up here. That's steric. And you could say to yourself, well, wait a second, Dr. Hill, you've drawn it so it's approaching that methyl group. It could come around from the other side. Well, on the other side, we've got this ethyl group here, right? So no matter which way we're approaching this big bulky group is going to interfere with either the ethyl group in this case or the methyl group on the other side. So whenever you're trying to remove one of those internal protons, big groups do it very poorly. So with Hoffman products, you can use a bulky base. So if you had, as an example, let's redo this. So conditions for a Hoffman elimination would be you would use tert butoxide. Usually comes with potassium. Tert-butanol is a good solvent. What we're going to see is protic solvents are good for elimination. And this will favor the formation of your terminal alkenes. This is a terminal alkene. Because the double bonds on the terminal end of your chain, right? So these are Hoffman conditions, Hoffman. And there are a number of different big bulky bases that we talked about. Tert butoxide's probably the easiest to manipulate. There are some other ones that are really strong bases, like on your LDA is another example. This is a very strong base because it's effectively nitrogen with a negative charge. LDA, the solvent for LDA is always going to be something like THF or ether. It has to be an aprotic solvent. And the reason is simple, because it would react with the solvent if it was if you had like tert-butanol in there. The first thing that is going to happen is that the negative charge between the nitrogen is going to grab the most acidic proton, and you're going to make plus your, in this case, you'd make tert butoxide. But if you were using methanol or water, then you would make something, you would make hydroxide or methoxide, right? So you're always going to use an aprotic solvent with something like LDA, or the other one, which is a big bulky base, which is super reactive, is tert-butyl lithium. Tert-butyl lithium. This would need an aprotic solvent as well, because that's carbon with a minus, right? So just keep in mind, if you ever see LDA or tert-butyl lithium, they are always in aprotic solvents because they would react with the solvent. You put tert-butyl lithium in with water and you're going to make a big explosion. Okay, so with Hoffman conditions, what you want to use is basically a big bulky base. So you want to use a bulky base. And you can form the terminal alkene. With the Zetsiev's conditions, you want a non-bulky base. And the easiest ones to use are things like methoxide, ethoxide, or even hydroxide, I suppose. The one disadvantage of hydroxide, and the solvent you're going to use in each case is going to be the conjugate acid of this base. So with methoxide, you're going to always want to use methanol. With ethoxide, you're always going to want to use ethanol. And with hydroxide, you're always going to want to use water. And there's a couple good reasons for this. One is that, remember, there's a very loose equilibrium between so let's say you have methoxide in methanol. Well, this is going to be in equilibrium with methanol plus methoxide. If you had methoxide in water, for example, well, now you're going to be in equilibrium with methanol and hydroxide. And this is just going to complicate your reaction. So whenever you're using like a tert butoxide, you're going to use tert butanol. Whenever you're using methoxide, you're going to use methanol. Whenever you're using ethoxide, you're going to use ethanol, and vice versa. So hydroxide doesn't, because its conjugate acid is water. Water sometimes has a hard time solubilizing some organic compounds. So normally you would use methanol or ethanol just because it helps solubilize all the reagents you're going to use. So hydroxide can sometimes be problematic. So that's basically what we're getting at here. So to do the Zetsiev product, we had the exact same compound here, X. We would just use methoxide and methanol, or, you know, ethoxide and ethanol, and this will give us our two Zetsiev products. So Zetsiev rule is that you basically form the more substituted alkene. So and to do this practically, you want to use a smaller base. If there is an opportunity for 2 protons being removed. So in some of the examples previously, there was, because the stereochemical requirement meant that 2 groups had to be axial, there was only 1 proton there, that you're only going to form 1 product. But when you've got a chance for more, you use a smaller alkene. Okay, so I'm going to stop here, and then I'm going to restart talking about E1 eliminations a bit.